For the lack of a better word on what to call this lesson, I am naming it Lesson 8 of Module 1. And what the lesson is really about is just to highlight a few things, not necessarily putting the test scripts in front of us, but just to highlight the common mistakes that we're making so that when we write again, be it an exam or whatever the case is, you guys know more or less what is expected of you and where most of the errors were happening because you were writing different scripts. I've tried to collect all the commonalities that were happening and I want to emphasize on those. So for chapter 1, the following needs to be noted. The first one I want us to look at is on your line-to-line voltage naming conversion. What do I mean by naming conversion? I mean, what do we call our voltages? Who are they? So that when you guys see a reference voltage, you must know, is it what we usually call the voltage or is it not? So I'm going to start with the delta connection. You can see there's a triangle at the bottom and we're going to go there to name these voltages. Okay, so for your V line to line, or what we just call as a line voltage, this is the following. Between phase A and B, in a clockwise direction, such as the arrow that I've just put that is thick and black, clockwise. And this is to be noted because it's different from our anti-clockwise of our positive and negative phase sequence. When we name our voltages, we go in a clockwise direction to name them. So clockwise, we go from A phase into B phase. So that's why that voltage is called VAB. And then looking at your VBC voltage is coming from phase B going towards phase C as per the arrow that I've just drawn. Don't be confused by the arrows looking on both sides, which is just showing that those are your phase voltages as well. The arrows I want you to look at are the thick ones that are in black, where I've written the name of the voltage above the arrow. Then for our last voltage, it is called VCA, and it is coming from C phase going towards A phase in a clockwise direction. That's why then our voltages are named VAB, VBC, and VCA in that sequence. Then I want us to look at your star connection. And in your star connection is still the same thing. So your A phase is at the bottom here and your B phase is on the left-hand side. And going from A to B, that voltage is called VAB. And then again, going from B phase to C phase on your left to your right-hand side, that voltage is called VBC. I'm moving in a clockwise direction. And then on the last one, from the right-hand side to the bottom, where I've got my C phase and my A phase, that voltage is called VCA. So now, if you are given voltages that are named VBA, VCB, and VAC, you need to know these are not how we call our voltages. All right? So therefore, what this means is that in order for you to go back to our normal voltages, which is VAB, VBC, and VCA, I must add 180 degrees to whatever the angle I'm given of VBA or VCB or VAC. Therefore, if I've got VAB, I must know that it's actually equal to my negative VBA and vice versa. So if they had given me a VBA, you must know that that VBA is actually negative my VAB that I know. So in other words, I must now go and add the angle of 180 degrees in order to convert the VBA that they've given me back into my VAB that I know, or VBC that I know if you look at the right hand side where I made the example with VCB and VBC. And then similarly at the bottom, I've got for VCA, which is equal to negative VAC. So it's actually equal to VAC in the angle that comes with VAC, and then I need to add 180 degrees. That's how I get to my voltage, the name that it is named. So in the test, a lot of us made the mistakes where we were given the inverse of the voltages that we know, and then we took those and utilized them in order to do all our calculations, and therefore everything was incorrect because we were just out of phase with everything that we did. Then I want us to remember our relationship of our currents. What are our line currents? Because I've been asking for line currents in most of your guys' questions, and some of you would leave it where you had given me IAB or IBC and ICA, and you leave your answer there. And your answer there is not complete. So if we have a star connected load, then we must know that our line current and our phase current is one and the same thing. As you can see with the gray and the red arrows, that your IA is the same as your IAN, which is your phase current, and your IB, which is your line, is the same as your IBN, which is your phase current, and so is your IC. So for a star connected load, we usually know that your line current is the same thing, okay, as your phase current. But when we get to our delta loads, then you can see there that there is your line currents are IA, IB, and IC. Those are line currents, all right? So therefore, your phase currents here are your IAB, IBC, and ICA. And now if I'm looking for my line currents, I must go then, because you would have probably worked out what your phase currents are from all the different questions that would have been asked there. So then to get your line currents, which is the final answer that they're looking for, you would go and say your IA, which is equal to, and you look at the node on top at A. You can see that your IA is coming in. What is going out is positive, that is IAB, and then the other one that is coming in will be negative, which is minus ICA. And you do the same thing for your B node and the same thing for your C node. So you must study that your IB then equals to IBC minus IAB, and your IC is ICA minus IBC. Then coming into Millman's theorem, what we need to notice here and recall is that your VCN utilizes your phase voltages, okay? It doesn't utilize your line voltages, guys. It utilizes your phase voltages. So if you're given a reference, which is your line voltage, either it's an AB, BC, or CA, you must know that that voltage needs to be divided by the root of 3, and you must draw your angle accordingly so that you know if it is in a positive or a negative phase sequence, that it will either lead or lag your line voltage that you have been given. So the common mistake made is that people went and utilized their line voltage angles into this equation, although they knew that you must divide those line voltages by the root of 3, but their angles, they didn't change them. And then obviously the other ones made the mistake that I've already explained on the naming conversion. Okay, you are given a voltage that is unfamiliar or foreign because your VBA is foreign, your VAC is foreign, and your VCB is a foreign voltage. So you were given those and you went ahead and drew those in with the ones that you know, and then went and did your EAN, EBN, and ECN. So obviously your angles were also incorrect there. So the first steps, making sure that you get your voltages corrected. Once you've now worked out VCN, then you must know that you go and work out your VAS, your VPS, and your VCS. And those will help you in order for you to work out what your line currents are going to be. So if the question that you are given has got a line voltage in it, then it means you obviously need to find the phase voltage, as I've said, and its angle depending on your phase sequence. And then you use that VAS, VBS, and VCS to find your line currents, as I've said. Then, if you were asked to do the power calculation with those line currents, the formulas where your voltages are written either VAN or they are written VAB, you don't change those voltages, they remain those. So you don't go and replace your VAN with VAS. The only thing you utilize there is your line currents, which is what you have worked out from the Millman's theorem. So let's go to the next slide so that it becomes clearer. So here I'm showing you that basically your VAB would have still been your line-to-line voltage that you had initially, as so as your VCB, you must remember that is your VBC at 180 degrees plus of that angle, which would then, if you had to simplify it, your VAN will still be your normal phase voltage, your VBN and your VCN. They are not replaced by the voltages that you find on Millman's, which is your VAS, VBS, and VCS. Instead, your line currents, IA, IB, IC, are what you are going to utilize when you calculate your power, which you now got those from Millman's theorem. Then the second thing I want you to just note, because I had questions where I drew in your wattmeters, and we are so used to our wattmeters being on A phase and on C phase that if it becomes on B phase, we do not know what to do. So I want you to note this, what I've just put at the bottom now. And it says here that your first wattmeter will be connected with a lagging power factor, which is why you just have your VAB and IA the normal way, and you say your VAB minus your IA, whereas your second one will be connected with a leading power factor. And that is why your voltage naming conversion changes by 180 degrees, because you are now going to a capacitive type of load. That's why we no longer put VBC, instead we put a VCBN. So if you had to have now between your A phase and your B phase, that's where you have your wattmeters. In other words, it's a W is equal to WA plus WB. Then it means that you still have your WA the same way, VABIAB, but your WB would be VBAIB. Okay, and that would still be equal to what you have on top, where it is a VANIA plus VBNIB plus VCNIC, if you were just calculating it, not utilizing the two connected wattmeters in it. All right, so I needed to emphasize that so that you know if you get given in an exam or in the test that we had someone given it as WA, sorry, plus WB, that you know that on your WB it becomes VBA multiplied by your current IB. Then we had an example that we did on our lessons, and I think it was the lesson that talks to your delta to star conversion. And there we went and did it in steps on what you are required to do. That the first step you do, you put in your impedances right in the middle of your triangle so that you do your conversion. Then after you've done that conversion, and you must remember the conversion, so for the top part where you've got ZA is going to be the two adjacents divided by the total of all those impedances that are in that triangle, and so you go on each side. Then we know that once we have it, we can now draw it as I've put in here, and I can say my ZA total becomes the one that was in series plus now what I've just worked out, and so is my ZB and my ZC. Once I have got those, then I go back to whatever voltage I've been given so that I can be able to work out what my line voltages relevant naming are going to be, and therefore my phase voltages. And I utilize those to go and work out my VAS, VBS, and VCS. Only then I can be able to work out what my line current is. So some of you that were given exactly a similar exercise, you skipped the step of going to Millman's theorem, and it wasn't specified. So you must know you just need to go right into it without being told. Okay, so you guys, after you had your ZA total, ZB total, ZC total, which we did just fine, you then just directly went, because you had your EAN and EBN and ECN, and utilized those to find your line currents. And it should have actually triggered something for you, because unlike the tutorial you were given, they then said utilize the same type of network you've done now, where you're connecting your wattmeters to your A phase and your C phase. And you would have seen that your two powers did not balance out. So that is important. So even try this one that we did in class, but make sure that your power is balancing out when you are just doing your PA plus PB plus PC, compared to when you are utilizing your WA and your WC. Okay, and then while we are talking about the power calculations, I want us to just note this following, that although our voltages and our currents in your star or your delta connections have got different values in them, when we actually write the power calculations, they come out to be the same. But although they're coming out to be the same, those values are not necessarily the same or mean the same thing for each of those circuits, be it a star or a delta. And what am I talking about? Because now I'm talking in circles, right? So let's go to the next slide to see. So here you've got a star circuit. Ne. So in a star circuit, you get given a voltage. You must know that because it's a star, your phase voltage is the same as your line-to-line voltage over √3. All right. So your phase voltage is your VAN, and your line-to-line could be your VAB or your VBC or your VCA. So it becomes that line-to-line over your square root of 3. So that is your what you call your voltage in your star connection. Then you have what we call your current in your star connection, and we know that that one is the same as your line current plane. Then your impedance of your star connection would simply then be equal to your voltage in that star connection divided by your current in the star connection, which if we take it back to your line or to your phase conversions, it will be your VL divided by your square root of 3 IL. Okay, the VLL or VL is what we had under that V star, which was the VLL over the square root of 3. So you've got that, and then they multiplied it, they divided it simply by your IL. So therefore then your star, which is your complex power, becomes 3 times the voltage multiplied by the current. All right, so it's just that voltage star and that current star. Okay, and that voltage star, you can obviously now see that is your phase voltage, and that current star is actually your line current as well. And that would be enough. You can do it using that. Or if you're going to go into your line to line phenomenon naming, then that simply becomes your square root of 3 VLIL. And then your power, then your P and your Q would follow the same sequence of that square root of 3 VLIL cos your theta, or if it's a Q, VLIL sine your theta. Okay, so you could have used that, or it could have just still been that 3 V star I star cos theta, 3 V star I star sine theta. Then in your delta conversion, you must just remember that your delta and your line voltage is one and the same thing, and your delta current that we refer to in there is actually your line current over the root of 3, because your phase currents are different from your line currents in a delta scenario. And then you can see your Z delta is your V delta over your I delta, which is actually equal to square root of 3 VL over IL, instead of the one that you had for Z star, which was VL over square root of 3 IL. You see the difference between those two. Then your S delta, you can be able to get is still your 3V delta I delta, or square root of 3 VL IL. And so you can be able to work out your power and your reactive power in your delta configurations. Now, the example that some of the guys were given, and I've just taken from one of the tests, okay, because your resistance and your inductance were not necessarily the same values. So they give you a network where they say your loads are identical. So it means that your Z star for all your phases is the same, and your Z delta for all your phases is the same. And they say that it's connected first to a star connection, and then second into a delta connection. And they want us to prove that the total power in our delta connection is actually 3 times more than the power in the star connection. So your power being P, all right? You go through the steps. You don't have to work out VAB, VBC, VCA like most of the guys that had this question went and did. Because why? You've got a balanced load. So therefore, you only need to work out on one phase, and you know you can either multiply by 3 or just use a square root of 3. And you've got your answer that would be for your 3-phase circuit. That's the first thing. Then the second thing, if you are in a star connection, all right, you must remember that 380 you were given is your V star. No, that 380 you were given is your line to line, because we always assume that you're given a line to line voltage. So your V star would be your line to line over your square root of 3. Okay, and your I star, we know that will still be the same as your I line. How do I find my star or my current? My current simply becomes my V star over my Z star. Your Z you've got is your 15 plus J 2 pi F 39 times 10 to the minus 3. Okay, that's your Z. So you take that V star, which is that VLL over root of 3, and you divide by this Z, and that will give you your I star. But you know that that I star is the same as your IL. So now effectively you've got your IL and you've got your line-to-line voltage, because you're given to it as your 380. You can automatically go already to your power. And your power is your P power star is equal to root 3 VLIL cos theta. Okay? Or you could have said is that V star. And what was that V star? It was your VLL over square root of 3. So it would be 3 multiplied by VLL over root 3 times my I star. And then you could be able to get what your answer is going to be. Then you now go to the delta scenario, which is on the right hand side. You still have exactly the same impedance that you're using into the system, and you do the same thing. You are given your V line to line, and you know that is exactly the same as your V delta in this case, all right? Then you need to go calculate what your I delta is going to be. And how do I find my I delta? I know that my I delta is going to be that V delta that you've been given, and I divide it by the Z delta that you have, which is the 15 plus J 2 pi F times 39 times 10 to the minus 3. I get my answer of my Z delta, and I can utilize that, of my I delta, and I can utilize that to convert it to my IL. How do I convert the I delta to my IL? My IL will simply be my square root of 3 times my I delta, and I get my IL. Once I now have my IL, I can go directly to the P delta formula. Square root of 3 times my VL, which is the 380, times my IL, which was my I delta times my square root of 3, cos my theta. And then when looking at the two answers, you will simply be able to tell if your delta is 3 times your star load or not. And that is how the answer gets answered. So we went about the long way of going VAB, VBC, VCA, and it just got very, very long. And in a test or an exam, you would not have had that much time. You must remember what I have just put in front of you. And that is it, folks, for chapter 1 on the test.